Thank you very much for inviting me. And so today I'm going to speak about this this topic that's part of my PhD thesis. Is like a half of my PhD thesis that I finished in September. And so let's start with some setting and what are these objects that I'm interested in. So subjects are of this sort. So there are proper holomorphic submersions from some smooth projective variety, some projective manifold y hy over bl, where it's important to stress that all the fibers in this submersion are smooth. So the base, the total space, but also the fibers are smooth. And we fix an ample line bundle L over the base, and also relatively ample line bundle hy over y. So this means that the restriction of hy on each fiber of the fibration is ample. And so why are these fibrations interesting? So one first way of seeing them is because they generalize holomorphic vector bundles in a way that I will now make a bit more precise. And also they constitute a way of studying families of projective manifolds. So moduli theories have essentially two goals. One is to classify objects of some type, and another one is to study how they behave in families. And so studying these fibrations is a way of approaching this second goal of moduli theory, in a sense. So vector bundles, if we fix a homomorphic vector bundle E over base B and assume that it's simple, so it doesn't have its endomorphisms have only one-dimensional global sections, then we can construct a holomorphic submersion by taking its projectivization. So for each fiber, we take the projectivization of that fiber. And so this is we can construct a relatively ample line bundle on it, which is the dual of the tautological bundle. So this means that let's see if I can write something on it. So it's on each fiber. So this line bundle on each xb is just the tautological bundle. It's like the hyperplane bundle on that fiber, so on PEB. And so you know that the famous Hitchin Kobayashi correspondence establishes an equivalence between an algebraic geometric stability condition, that's a slope stability, Mumford stability, and the existence of an Hermite Einstein connection, which is I will write the definition in the next slide, but it's a geometric PDE, so partial differential equation that involves a curvature quantity associated to some connection. And so this so one a goal. So both these notions induce. So give a construction of moduli spaces of holomorphic vector bundles. And so a goal of my talk and of this project is to construct a moduli space of holomorphic, of smooth fibrations or homomorphic submersions. And doing this using a generalization of Hermite-Einstein connections to what are called optimal symplectic connections that I will, of course, explain what they are afterwards on these fibrations. And there will be also a notion of stability involving case stability on the fibers of these fibrations. The idea is that if you take like projectivization of holomorphic vector bundles, the fibers are just projective spaces, so they're like they are nice spaces in a sense, but if you take some general fibrations, then we need an extra stability condition for the fibers that cannot be too wild. And this stability condition is given in terms of K stability. So let's stick with vector bundles a little bit more. So if you take a vector bundle, holomorphic vector bundle, let's say over a curve, and fix Kähler form on the curve, then we can define the slope of the vector bundle as the degree divided by the rank. And we say that the vector bundle is stable if the slope of E is strictly greater than the slope of every of its subbundles or subsheaves if you are on a higher dimensional base. And it's semi-stable if equality might happen. And so it's a classical result of Mumford that there exists a Moduli space of semi-stable vector bundles when you fix rank and degree, and this Moduli space is constructed as a GIT quotient locally and in this case also globally. And a similar construction can be done in the case of from the geometric side point of view, so from the Hermite-Einstein point of view. So if you take Hermitian structure and Hermitian metric on E, this is an Hermitian inner product on the fibers of E, and so we have E over B and H on the fibers of E. This induces a connection, a charm connection on the fibers, and this connection is Hermite-Einstein if it satisfies this equation, where on the left-hand side we have the curvature of the connection, and so it's this F denotes the curvature, and so this is equal to some multiple of the identity. So it's constant in a sense, where the constant is given by the slope, so it's a topological constant. And also from this point of view, so looking at Hermite-Einstein connections, it's a result of Fujiki and Schumacher that it's possible to construct a Moduli space of vector bundles that admit a Hermite-Einstein connection. And of course, through the Hitchin Kobayashi correspondence, these two Moduli spaces are related. So if we now go back to the fibration setting, now I will explain how to sort of generalize this picture in the case of more general fibrations. So in the case of a fibration Y over B, we need first a generalization of Hermite-Einstein connections, which are these optimal symplectic connections that I will explain later. And so these are essentially solutions to a PDE, and to a geometric PDE that involves different curvature quantities on the fibration, and they are so related to a sort of global stability of the fibration. While and then we also need, as I said before, a stability condition for the fibers, and this will be given in terms of K stability property for the fibers. So maybe another little bit of motivation before I go into some more technical details. So as I said before, we have the Hitchin Kobayashi correspondence that relates, so establishes an equivalence between slope stability and the Hermite-Einstein PDE. And then from the K stability side, we have the Yautian-Donaldson conjecture that establishes sort of a similar equivalence between an algebraic geometric condition of stability and the existence of Kähler metrics with constant scalar curvature, which I will abbreviate with CSCK, and these are also solutions to a PDE. That's a scalar curvature of some Kähler metric is a constant, and so some motivation behind the study of these fibrations is to understand how these two pictures, these two equivalences interact with each other. So the main result that I will discuss today is this, so that there exists a Moduli space that parameterizes holomorphic submersions, pi y from y hy, where hy is a fixed relative polarization, to some base with a fixed also line bundle, that satisfy these two conditions. So they have discrete relative automorphism group. So the automorphisms of the fibration that commute with the projection is a discrete group, and also they admit an optimal symplectic connection. And this Moduli space is a Hausdorff space, and it's a complex analytic space, and it also admits a Kähler metric that is a Weil-Petersson type Kähler metric. So let's start with the stability of the fibers condition. So this is given in terms of analytic case stability. So we require that we assume that our fibration y over b degenerates to a fibration x over b, where the fibers of x, so for each on each fiber there is a constant scalar curvature metric. There's a Kähler metric with constant scalar curvature. So we have some omega b in the first Chern class, so representative of the first Chern class of the relative polarization of x restricted to the fiber, such that its scalar curvature is constant. And so this constant is in a topological constant, so it is independent on B. This is because the first Chern class, if you view it as a cohomology class, it has integer coefficients, and so while the fibers, nearby fibers, are to be thought of as deformations of each other, and so the class stays the same and on all fibers, and so this constant is independent on B. And also it is a result of Dervan-Seknon that also is based on builds on the deformation theory of constant scalar curvature metrics, that it is possible to construct a global two form on X that restricts to a constant scalar curvature metric on each fiber. So from each of these omega b we can actually have a global omega that's relatively Kähler. So I will say that omega is relatively Kähler metric. And every time I say that something is relatively or holds relatively, I mean that it holds when restricted to the fibers of the fibration. So what does degeneration mean, really? It means that we can find so that we can construct a family like this, so curly x curly h over b times s, where s is some parameter space. You can think of it just as C or some curve in C, or such that for S equals 0, so at a special point of this parameter space, we have the special fibration x over b, and at every other point S, the fibration is isomorphic to our original y over b. So this is the special one, so the relatively CSCK one, relatively constant scalar curvature. And so we can think about this, although it's not really necessary to assume this extra assumption, but a way of thinking about this is to assume that we have C star action on B times C or B times S that acts trivially on B, and then we can lift this sister action to curly X, curly H. And so in a sense, we can think of this as a family of task configuration. For each fiber, we have like a task configurations. For those who know what a task configuration is, that is compatible with the fibration structure, so with the projection, and with the fact that we have a holomorphic family. And so yes, but this is a way that we can think of this family as all the fibers are the same except for the central one, which is the special one with constant scalar curvature fibers. So this means that the fibers are analytically K-semi-stable. So this is what I mean when I say that we want a stability condition on the fiber that comes from K-stability. So in particular, the constant scalar curvature metrics are K-polystable, and in this case we don't have a constant scalar curvature metric, but we can degenerate to it. And so the fibers are analytically K-semi-stable. And also a relative version of Hermite's fibration theorem implies that as smooth manifolds, X and Y are diffeomorphic. So we can fix and underline smooth manifold, and essentially we can view Y as a deformation of the holomorphic structure, or the complex structure of X. And so, yes. And also, as I said before, the first Chern class of these relatively ample line bundles can be viewed as the same cohomology class when we view it as cohomology class on the underlying smooth manifold. And so these are so this means that the first Chern class of Hx is also of the right type, also on Y. And so what this gives us is that we can view, so we have this metric that we constructed before that is relatively CSCK, so it has constant scalar curvature when restricted to each fiber, and it belongs to the first Chern class of Hx. And we can also assume, using these remarks, that this is also relatively Kähler on Y, although it's not doesn't restrict to a constant scalar curvature metric. So in particular, yeah, as I said before, so this is a relatively CSCK, so it means that the fibers are K polystable. And so it means, yes. Yes, so we can fix, so the upshot of this is that we can fix omega and consider only the deformation of the complex structure of X to the one of Y. Yes, which is precisely this. So we fix the smooth structure, we fix the relatively, now it's a relatively symplectic form and or relatively Kähler form, and we vary the holomorphic structure. And I represented it like this. So we have X that is given by smooth manifold with symplectic form and complex structure J0, and Y, which is isomorphic to all the other manifolds or all the other fibrations in the family, that is given by M omega and the family of complex structures JS that are all isomorphic except for the 0, 1. And yes, so this can be made more precise by this theorem that allows us to give a parameterization of all the deformations of X. So the deformations of the holomorphic submersion, so of the holomorphic structure of X over B, that preserve both the projection onto B, so the basis here is fixed from the start, and so we always have to make sure that all these deformations and degeneration preserve the projection onto B, can be parameterized by some open subset, so by some space that is a finite dimensional vector space, so an open subset, open neighborhood of the origin in a finite dimensional vector space that is a space of 0-1 forms of with values in the 1-0 holomorphic tangent bundle. So if we were not looking at the Kähler form, but only at the holomorphic structure, this would be a space of deformations of holomorphic structure. So it would be like in the first cohomology of the holomorphic tangent bundle. But here, since we have also this compatibility with the Kähler form, it's not precisely the first cohomology of the holomorphic tangent bundle. It also has to take into account the compatibility with omega, but it's essentially this. And so we have a map that maps so from this finite dimensional space to the space of almost complex structures that are compatible with omega and also preserve the projection onto the base. And so yes, so and this okay, also this a map is equivariant with respect to the action of a group. That's the group of biolomorphisms of X that commutes with pi again, so that preserve the projection onto B, and are also fiber-wise isometries of the relative Kähler form. So this is a relative version of Kobayashi theorem, or is a version of Luna-Slice theorem, or a version of the Hilbert scheme for these fibrations. So where you want to preserve also the projection onto B, and well, in this case, you want also to preserve the Kähler form. So what this theorem, so Kobayashi theorem, says is that we can identify so our fibration X over B that I recall is the special one, so the one which is relatively K polystable or relatively CSCK, is the origin in this space, so 0 in V pi. And all the other fibrations in the family are given by some family Y of points, Ys. And we can view this Ys as an orbit in V pi for some one parameter subgroup of the group of relative isometries. So we have this orbit where the origin is in the closure of the orbit, and so all the other ones are biolomorphic, where the biolomorphism is given by this one parameter subgroup. Now the key to construct a moduli space of these fibrations is to have to prove that having a degeneration to a fibration with CSCK fibers is a locally closed property. So we want to find some locally closed subset of subvariety or subspace of V pi, such that if you take another fibration that is closed to this one, so if you move these points to nearby points, you still have this degeneration to something that some fibration with fibers have a constant scalar curvature metric. And so this is given by this by this. So it's more precisely stated like this. So we need an extra assumption, and this assumption is that all the fibers of X over B have the same automorphism group, or isomorphic automorphism group. And this is a technical assumption, but it's involved in many parts of this theory. And so once we fix this assumption, then we can find a locally closed subvariety, or such that for every point in this subvariety, the corresponding fibration, so the fibration that point parameterizes, admits a degeneration to some fibration x prime over B, where whose fibers have a constant scalar curvature metric. And yeah, so let's see a little bit how the proof of this goes. So it's a local proof. So we construct x prime over each chart of B, and then we glue them on B. So to do this, we consider the Kuranishi space of the fiber. So we fix one special point B naught in B, in this U, so in this open chart, and then we view all the nearby fibers, as deformations of that special fiber, and then so we have CSCK fibers nearby this special fiber are, for one thing, they are GAT polystable points for the action of the group of automorphisms of the fiber. But since they all have the same group of automorphisms, so we have this assumption that these groups are all isomorphic, these points are all fixed. And so we mean that means that we have this picture here. So here we have our fibration X over B, where each fiber is represented by a point, and all these points are fixed points. And then we have our fibration Y over B, where each fiber degenerates to a constant scalar curvature 1. So each fiber degenerates to a fixed point. So we have this sort of stratum of points that degenerate to a fixed point, so which have a fixed point in the closure of their orbit. And then the proof then follows from the fact that there exists an analytic subvariety of V of our space, like of the space that parameterizes deformations of this fiber over point B naught, such that this map that maps the semi-stable points to their fixed point in the closure of their orbit is a holomorphic map. And so then there are some results that ensures that the K polystable degeneration is actually unique, and then it relies on the deformation theory of constant scalar curvature metrics, and the fact that if you have a K polystable deformation of manifold with constant scalar curvature, this also has a constant scalar curvature metric. And for those who are maybe familiar with it, this is similar to the Biavenitsky-Birula stratification, which is essentially it's very similar. So it's a stratification of points that converge to a subset of fixed points. Although I haven't used that explicitly, but it's same ideas. And so yes, once we have finished this, so proven this result, this doesn't have anything to do with special metrics. It's just a GAT result. And now we can dive into more PD theory. And so so now we have fixed what it means for the fibers to be stable, in a sense, so the stability condition for the fibers. Now we need an equivalent of the Hermite-Einstein condition, and this is given by the optimal symplectic connection condition. So if we have Y over B, so a holomorphic submersion with k-semi-stable fibers, which has a relatively CSTK degeneration to a fibration X over V, whose fibers are constant scalar curvature, then we say that a relatively Kähler metric is an optimal symplectic connection if it satisfies this equation. So here, this, so maybe I can, this FH, rho H, and nu are all curvature quantities of associated to omega in various ways. So FH is the symplectic curvature, so it's something that does not depend on the holomorphic structure. Rho H is the relative Ricci curvature, so it's the curvature of the Hermitian metric induced by omega on the top wedge power of the vertical tangent bundle, so the relative canonical bundle. And then nu is a curvature of the deformation. So it's the derivative, second derivative of the scalar curvature, vertical scalar curvature of omega with respect to the complex structures JS that parameterize Y. So it means that nu encodes the curvature of the of how the fibers of X deform to the fibers of Y, or the fibers of Y degenerate to the fibers of X. So this equation was introduced by Dervan Saknon when the fibers have a constant scalar curvature metric, and so already have a constant scalar curvature metric. So we are in a special case where X is equal to Y. And here, this is an extension of this equation to when the fibers of Y are k-semi-stable. So this left-hand side is a smooth function, and so this PE is the projection onto global sections of a vector bundle associated to X, which are holomorphic potentials, or if you prefer, holomorphic vector fields on the fibers that vanish somewhere and can be written using some smooth function like this, so as the del bar, so as the gradient of some function. And to make sure that this is actually a vector bundle, we need to the assumption that we made before. So this assumption that these groups, the automorphism groups of the fibers, are all isomorphic, implies that this is actually a vector bundle, and this is a result of Hallam. And yes, so this assumption also is necessary to write the optimal symplectic connection equation. And so the extension of this equation to the case of k-semi-stable fibers is important, because having constant scalar curvature is not an open condition, and so in the construction of moduli space, you need something that is open. So if I start with a fibration that has constant scalar curvature fibers, if I take something that is a deformation of it, so it's it might not have constant scalar curvature fibers. And also, yes, this remark that this equation is interesting, or at least it makes more sense when the fibers have more automorphisms than the total space. And so, for example, it is trivial when the fibers are Riemann surfaces, because Riemann surfaces have discrete automorphisms. And so one way to maybe look at it, going back to the projective bundles, is that if you have a projective bundle and projectivize it as before, and take an Hermitian metric on it, then this Hermitian metric induces an Hermitian metric on the dual of the tautological bundle, and its curvature restricts to a Fubini-Studi metric on each fiber. But what happens is that Fubini-Studi metrics are not unique because projective spaces have many automorphisms. And so in this case, the optimal symplectic connection is equivalent to having a Hermite-Einstein connection. And what the Hermite-Einstein connection is doing is to fix this automorphism that allows us to choose canonical, choose the Fubini-Studi metric on each fiber in a canonical way. And so in this sense, optimal symplectic connections are like a canonical choice of relative Kähler metric on a fibration. So now assume that the automorphism group of pi y is discrete, so the automorphisms of the fibration, global automorphisms that commute with the projection is discrete. Then we can go back to our Kuranishi space, so the space that parameterizes the formations of the fibration. And we can write the equation like this. So we have curvature quantity, theta of omega. Then we have the origin of the space, which is the special fibration where fibers have constant scalar curvature. And then we have a vector, which is the vector that identifies the orbit that describes the generation of y over onto x. And so now let's assume that the equation is satisfied for y over b. And so we want to put everything together and construct a moduli space of fibrations that admit an optimal symplectic connection. And so assume that we have an optimal symplectic connection, so we have a solution of this equation. And then we take the locally closed subset of the first lemma, so the subset that parameterizes all nearby fibrations that also admit the generation to relatively CSCK fibration. And we ask, are these, or when are these also optimal symplectic connection? So when does this fibration also admit an optimal symplectic connection? And what happens is that if the automorphism group is discrete, then having an optimal symplectic connection is open. So it means that for every point in this W, and we can find a pair XV where X parameterizes a fibration with constant scalar curvature of fibers, and V represents the fibrations, represents the deformation of W to X. Then we can find a metric on this fibration such that the equation is satisfied. So we can find an optimal symplectic connection also on this new fibration. So then the proof is implicit function theorem result, and this lemma gives openness of solutions within the locally closed subvariety that was W. And so putting it all together, so let's consider y over b that admits an optimal symplectic connection, and then the two pieces of results, the two lemmas that I explained to you. This give a locally closed complex space. So before maybe I brought subvariety, but it's actually more a complex space where the equation still admits solutions. And so the local charts of the moduli space are given by this space W, quotient by the finite group, discrete group that turns out to be finite of automorphisms of pi y. So that's a discrete finite group. So this has some sort of an orbifold structure. And this is a Hausdorff space, and also has a Weil-Petersson type Kähler metric. And so in the end, there are some general picture about whether the optimal symplectic connection is also equivalent to some stability conditions. So as I said before, we have mu stability of vector bundle that's related to existence of Hermite Einstein metric. Then we have K stability that's related to existence of constant scalar curvature metric. And then so one can ask, are optimal symplectic connections also related to some sort of fibration stability? And there are some partial results in this direction by Darvan-Seknan and Hallam, and also Hattori, but they're not still conjectural, and possibly also the notion of stability to be used is also varies. And then another remark is that Archizuma and Hattori also constructed a Moduli space of Calabi-Yau fibrations, where in their case also the base changes, so it's a bit different from what I do, but in some case these two Moduli spaces are equivalent, and that's nice because their approach is much more algebraic and mine is a bit more analytic. And so yeah, I guess this is everything. Thank you.